bags. Only got $20 in my pocket. I'm hunting, looking for a come up. This is fucking awesome.
Fluid kinematics is a field of physics and mechanics concerned with the movement of fluids. Fluids tend to flow easily, which cause a motion of molecules from one point in space to another point of function of time. These fluids may be liquids or may be materials with fluid properties, including crowds of people and volumes of grains. Using quantum physics, fluids are classified into fluid particles, which are composed of numerous fluid molecules. These particles interact with one another and with the surroundings they are in. Fluid's motion can be described in terms of acceleration or velocity. Application in real world. One is taking blood pressure. 2. Making coffee. 3. Washing dishes. 4. Using lotion. And number 5 is using makeup.
Number 2. Define, compare, and illustrate the concept of Lagrangian and Eulerian descriptions in fluid mechanics. Lagrangian deals with individual particles and calculates the trajectory of each particle separately. In this diagram, consider the blue dot as a fluid particle with components to determine its position. As time passes, the position of this particle is changing, so as its components. Thus, position vector of x, y, and z coordinates are functions of time. The first derivative of the position vector is described as the velocity, while the acceleration is the first derivative of the velocity. Considering that there are many particles in a fluid, knowing each of their velocities are difficult. Then here comes the Eulerian. This deals with a finite volume called a flow domain or a control volume, in which the fluid flows in and out. In this diagram, consider that the fixed position 3D box is a control volume where fluid flows in and out. Instead of tracking individual particles, control volume is defined through field variables which can be scalar like pressure and temperature, or vector like velocity and acceleration. This can describe the particles that move in and out of the control volume. Therefore, the parameters are determined in a fixed position in a course of time and not the individual particles. That's all. Thank you!
So for number 3, illustrate the concept of the term material derivative in a simple graphics and how it is applied to field variables, linking Lagrangian and Eulerian description in fluid mechanics. So there are two descriptions of fluid flows, and that is the Lagrangian and Eulerian description of fluid flow. The first one is the Lagrangian description of fluid flow. It is where the particles or the individual particles are tracked and their positions, velocities, etc. are described as a function of time. And for Lagrangian description of fluid flow, individual particles are not defined. Instead, a control volume is defined. And these two can be linked together by the material derivative, also called as the total derivative or substantial derivative. The material derivative of some quantity is simply defined as the rate of the change of that quantity following a fluid particle. It is derived for some arbitrary property Q as follows, that is shown in the diagram.
So for number 4, define and illustrate what is flow visualization and what are the different types of flow patterns. So let us start with defining flow visualization. It is an experimental means of examining the flow pattern around the body or over its surface. So, it is an art of making flow patterns visible. At kung dili ang mga klaro nga pattern is gina-visible through experiment. So, there are types of flow patterns. Actually, there are two. The horizontal flow lines and the vertical flow lines. So, under the horizontal flow lines, there are 5 basic types. the I flow or the line flow, the L flow, the U flow, the S flow, and the O flow. While in the vertical flow lines, there are 6 basic types: the processing downward or upward, the centralized or decentralized elevation, the unidirectional or retractional flow, the vertical or inclined flow, the single or multi-flow, and lastly the flow between buildings. So that would be all. Thank you.
So, computation fluid dynamics is the study of how fluids flow using computers. The governing mathematical equations that explain how fluids flow are typically too complicated to solve using pen and paper mathematics and have to be solved on computers, often quite large computers. So, the importance of safety in analyzing fluid flow is that with the help of digital computers, CFD produces quantitative predictions of fluid flow phenomena based on the conservation laws such as conservation of mass, momentum, and energy, which is governing fluid motion. CFD has increased in importance and in accuracy. However, its predictions are never completely exact because many potential sources of error may be involved. One has to be very careful when interpreting the results produced by CFD techniques. The key to various numerical methods is to convert the partial differential equations that govern a physical phenomenon into a system of algebraic equations. Different techniques are available for this conversion. CFD is merely a tool for analyzing fluid flow problems. If it is used correctly, it can provide useful information cheaply and quickly. There are other kinds of numerical methods, for example, the spectral method and the spectral element method, which are often used in CFD. They share a common approach that discretizes the Navier-Stokes equation into a system of algebraic equations. An example of a software that executes this concept is ANSYS. ANSYS is a software which can be used for CFD. In ANSYS Workbench 13 or above version, you can use module of CFX and Fluent for CFD. ANSYS is the most complete software for CFD. In the version Workbench 16, you will have a more and intuitive configuration of parameters.
Number 6, letter A, derive and explain the Reynolds transport theorem for fixed CV. To convert a device analysis to a control volume analysis, we must apply our mathematics to a particular area rather than the individual masses. So, conditional conversion, it was explained by the Reynolds transport theorem. So, considering a fixed control volume through which a random flow pattern passes, in general, each surface's differential area dA will have a different velocity v and an angle with the usual to dA. So it is possible to find with the given figure here, which we have the inflow volume and the outflow volume. So for the conversion, we let B reflect any fluid property which refers to the energy, momentum, enthalpy, and others. And beta is equal to d beta over dm, be the intensive value of B per unit mass in any small elements of the fluid. These are the integral equations we will be using for us to arrive to our desired equation for the Reynolds transport theorem. So first is the total amount of B in the control volume, which refers to this equation. And next is the change within control volume and the outflow of beta from the control volume and the inflow of beta to the control volume. So by the way, the CV and CS refers to control volume and control surface respectively. So for the system shown in the figure, the instantaneous change of B in the system is sum of the change within plus the outflow minus the inflow, which refers to this equation, the instantaneous change of B in the system. With this equation, we note that the control volume is fixed in space, so the elemental volume do not vary with time. Also, we note that the V cos theta is the component of V normal to the area element of the control surface. Thus, we can write the equation into, and the vector form of the above equation is this equation. Thus, we can arrive to our desired Reynolds transport theorem in the vector form, which is this equation.
So, for Reynolds transport theorem for non-fixed control volume, we need to derive the equation from the fixed CV equation. So, as shown in the screen. So, in non-fixed control volume, note that we replace V by VR in this version of RTT. So where V sub R is equal to relative velocity, which equation is
So for question number 7, discuss the importance of RTT in the study of fluid mechanics and related courses. In fluid mechanics, it is usually more convenient to work with control volumes or open system, and thus there is a need to relate the changes in control volume to the changes in the system. The relationship between the time rates of change of an extensive property for a system and the control volume is expressed by the Reynolds transport theorem, or RTT, means that it provides a link between the system approach and the control volume approach.